Nickel catalyst applied to stereoform reaction. Potassium effect on the inhibition of methane formation. This work was written by Alan Taskin, Adriano Braga, Adriana Palhares, Alejandro Lopes Castilho, and José Maria Bueno. Steam reformer is a promising method to produce hydrogen, a clean fuel that presents as burning products only water and energy. The most used method to catalyze this reaction is nickel, a transition metal that has low price and high activity. However, due to its high activity, nickel catalysts lead to methane formation. Once the intermediates formed during the reaction are deposited at catalyst surface and then hydrogenated. Changing those catalysts with promoters as potassium has been described to avoid methane formation, although their effect on hydrogenation of intermediates CHX was not described before. The use of compounds that will form different CHX species during its decomposition will help to understand the role of potassium in avoiding methane formation. The goal of this work is to evaluate the potassium promoting effect on nickel, support manganese aluminate catalysis at methane formation during stereoform reactions of organic molecules through the hydrogenation inhibition of CHX intermediates and consequent its oxidation. The support was synthesized following the Sol-Gel methodology previously described by Avila Neto 2012. The wet impregnation was carried out with nickel nitrate as precursor in ethanol, and the same method was used to impregnate potassium using nitrate as precursor in water solution. The final samples were labeled with the total nickel weight, 8%, and amount of potassium vary from 0.5 to 5% in weight. The materials were characterized by BET surface area, X-ray diffraction, and Xanis in situ during reduction step, TPR with hydrogen, transmission with electron microscopy, XPS, and infrared. The catalysts were used at phenol stereoform and ethanol stereoform to analyze the effect of potassium at CH and CH3 species, and later the sample will be tested at butanol stereoform to elucidate the hydrogenation of CH2 intermediates. The theoretical calculations were performed by Professor Alejandro to analyze the system stability. The X-ray diffraction technique during reduction step showed that potassium presence decreased the nickel oxide temperature reduction more than 15 Celsius degree, since the first peak of metallic nickel can be solved probably due to the more oxygen vacancies caused by potassium promotion that change the support nickel oxide interaction. The same behavior already described previously can be noted for Xanis data. For potassium promoted samples, nickel metallic species begin to appear under 100 Celsius degree, while the sample not promoted, the reduction process starts above 150 Celsius degree. The thin analysis was used to confirm the particle size increasing. The same scale was used to highlight the difference between the nickel sample and those promoted with potassium. The first sample presented the smallest size, 6.5 nanometers, while the last one with high potassium content has 13.3 nanometers in average. The prepared catalysts were applied to phenol stereoforming to verify the CH species under hydrogenation. Once under normal conditions there are no methane formation. The catalyst 8 nickel presented high selectivity to methane above 60%, although the promotion with 0.5% of potassium already decreased to less than 40% the selectivity to methane. The sample with 5% of potassium reduced the selectivity to less than 10%. It shows that potassium effects to avoid CH hydrogenation, allowing the oxidation to form CO and CO2 by water gas shift reaction. The ethanol stereoforming was used to check the effect of potassium in CH intermediates. Without hydrogen, only can be observed decrease of nickel temperature activation, as described by Xanis data. Then, with hydrogen feed, the potassium presence allowed the stereoform at low temperature, promoting oxidation, but at high temperature the potassium effect at methane inhibition is modest. Summarizing the experimental results. To evaluate the effect of potassium to avoid CHX species hydrogenation was chosen three compounds to styrofoam reaction. The first, phenol, that presents CH as intermediate during its decomposition at the nickel system during styrofoaming, and under hydrogenation as expected methane is formed, while at nickel-potassium system the CH will suffer oxidation forming CO. Furthermore, by warm gas shift can generate CO2. For ethanol styrofoam that generates CHG species, under hydrogenation the system nickel-potassium didn't avoid the methane formation, suggesting that potassium is not able to protect the CH3 species, while is susceptible to form methane. Then, next step, the butanol styrofoam which forms CH2 during its decomposition can elucidate if potassium will be efficient to avoid the hydrogenation of those species and methane formation, since already described that at the nickel system methane is generated. Then, no significant change with potassium promotion at systems that generate CH3 intermediate is notable. Taking account the influence of potassium at CH species oxidation pathway, its presence decreases the energy necessary to promote CH oxygenation, forming CO easily when compared to nickel system not promoted. The theoretical calculations were done by Professor Alejandro to check the system carbon hydrogen nickel potassium stability. It was concluded that for CH system, more potassium offers high protection to CH group once it presents high energy. For CH2 system, the potassium seems to offer protection to CH2 group, but less than to CH. And for CH3 system, potassium does not present protection to hydrogenation. Conclusions: the effect of potassium suppression of methane formation is strongly dependent on structured organic compounds. For intermediates as CH and CH2, potassium is efficient on suppressing hydrogenation to methane when an aromatic is used, as phenol, whereas in linear compounds such as ethanol, the effect of potassium is modest. Some tests with butanol still will be performed to check the effect of blocking CH2 intermediates hydrogenation. System nickel-potassium decreases the energy to CH oxidation, which favors the CO formation. The DFT calculations indicate that potassium interacts with nickel surface in the way that increases the rate of adsorption of CH and CH2, which avoids the full hydrogenation towards methane.